we're looking at rate of change, more specifically known as connected rate of change. So here's just some little note section that we have here. So we're saying here that given three variables, we have x, y, and t. dy dx represents the rate of change of y with respect to x. Dx dt represents the rate of change of x with respect to t, and dy dt represents the rate of change of y with respect to t. Now, the moment we have rate of change, right? If you just use rate of change, it will be respected to t, right? There are ways that we could put together to get things when you connect rate of change. For example, given that you have those, we want to find a dy dx. You could see that we could put together dy. You put in together dy dt, all right? And if you divide that by dx dt, and then you do your math, you're able to get that. Basically, what we're saying is this. In a shorter way, if you have dy dx to be found, you will be given a rate of change already. For example, I might have been given dy dt. When you look at this, I need to have something be multiplied by this with the dx in it, so that when I cancel, so I need to cancel dt dx, but I'm going to cancel the t's so that the dy and the dx can remain, as numerator, denominator. So we're always looking for something that can be canceled, but you will always get one of them, and then you have to find a way to get the other based on the situation. In doing so, there are a number of things that we want to take note of. For example, we want to follow the following steps. One, you want to identify all variables clearly. You want to state any rates of change given. So they will have to give something. We want to state clearly what we need to find, definitely. And then we want to identify the connection among the three things that we're dealing with. So that will, eventually give us that last, piece of material to go. So let us look at some questions. That's the best way that we can really understand these. All right. So here is a question. So the question reads, right? So the question says, a cube is expanding in such a way that its sides are changing at a rate of 4 meters per second. 4 centimeters per second. So you're talking about the sides. So I'm going to highlight some stuff. The sides, right? So it's going in such a way that the sides are changing at this rate. So let us say we have a cube and we are dealing with the cube. Depending on what we want to use for the sides, you could use anything. Let us say I use X as the sides right now. I could use L, anything I want to use. So we're saying that the sides are changing, right? So what they just gave us dx dt, because we got let me read again. A cube is expanding, right, in such a way that its sides, so we get that the length of the sides are changing at a rate of 4 meters per second, 4 centimeters per second. So we have dx dt, x is referring to the sides, right now. So we have 4 cm. So we have that. Find the rate of change of the total surface area. So this is what we want to find. dA dt. A refers to area, T, rate of change, time. We don't know this. What we want to find is when the volume is at a certain place. Volume must be 216 cm cube when this is happening. All right. So then what we want to do now is to make the link. All right. So let us just look at what we have. Let's take a quick look. This is what we have. We have to find dA dt. But at the same time, we were given dx dt. The t is okay with me at the bottom, but I need to cancel something. I need a at the top, and I need this. So I need dA dx so that the dx could cancel, leaving me with dA at the top and dt at the bottom. That's what I want. So remember that I know what this is already. This is 4, should say. That's 4. I only need to find dA, all right, dx. So what I'm going to do is to take this and look at it. What is the total surface area of a cube? Well, we're talking about the total surface area of a cube. It's actually 6 faces, and the area of one face is x times x, which is x squared. So we're talking about one of this, and we're going to be having it 6 times. So then that's the total surface area. Now, if I differentiate this, I'll get dA dx, which is exactly what I want. And it's going to give me 12x. dA dx is 12x. So now I'm able to find the plug for this, because I am now finding dA dx to go there. But at the same time, x is going to be in my expression. X refers to the length of the sides. But remember though, I could now find what the length of the side is, because we are supposed to be doing this when the volume is at 216. Now let us put this in calculation. 216 should equal to the volume. How do you find the volume of a cube? X times x times x, which means x to the third. Now, if I take the cube root of this, I'll definitely get 6, which is equal to x. So what I'm suggesting is I now know the value of x when the volume is 216. So the final response is this. dA dt is going to equal to 4 times 12x, but x is 6, right? So basically 12x, x is 6. So we need to put that on our calculator. We're talking about 4 times 12 times 6. So I'm getting a total of 288 centimeters square per second. And understand the unit. We're dealing with area with time. So that is the rate of change of the surface area of the cube when the volume is at 260. Let's do another one. All right. So here's another question. So this one says that 2 variables, x and y, right? So we have 2 variables, we have x and we have y, are connected by the equation y is equal to 4x into x plus 2. If x is increasing, so now we're getting x, we're getting dx dt, because they did say x is increasing, right? So dx dt is actually 2 units per second. So we just got it that x is increasing at a rate of 2 units per second. Find the rate of change of y. Find the rate of change of y at the instant when x is 6 units. So you want to know what is dy dt. You notice the moment there's a rate of change, t is going to be at the bottom. So dy dt, we don't know. But we want to know it when x is equal to 6 units. All right. So what we want to do is to firstly take this system that we have. All right. Remember that y is given as 4x into x plus 2. What we want to do is to apply our regular law of distribution, right? So we're going to rewrite this as y is equal to 4x squared plus 8x, right? And then now we can find dy dx. So we're going to differentiate this. It's going to give us 8x plus 8. All right. So that is it. Now let's put together what we want to find and stuff like that. So let us take a quick look. My intention is to find the dy dx. They gave me dx dt. It simply means that I need to have a dy at the top and a dx at the bottom, such that the dx cancel the. You do notice that we have dx dt already. It was given as 2 units, so this is 2. We know that. So it's now my intention to substitute. But at the same time, I can find the value of dy dx, which is this, when x is 6, because we were told 6 units. So let's just find that. So we're looking at, so let us just look at this. We're looking at dy dx, right, which is 8x plus 8. 8x plus 8, let me fix that, 8, yeah, thank you. And we're looking at it where x is equal to 6. So this is actually 8 times 6 plus 8, 48 plus 8 is going to give us about 56. So now, basically, what we have now is 2 times 56, because this is dy dx, 56. So it's going to take this place right there. So 2 times 56 will give us 112, right? Find the rate of change of y, right, at an instance when x is 6 units, right? So it's 112 units per second, right? All right, there you go. It's another one. So you have to take a look, see what you have, find the connected rate of change. All the time there is a connection, right? Let's go to another question. All right, let's go. All right, so for this question here, it says a spherical ball is being inflated at a rate of 40 centimeter cube per second. So this is volume right now. So what they gave us right now is dv dt. This is giving as 40 cm cube per second. Find the rate of increase of its radius. Find the rate of increase of its radius. So I need to find dr dt. I need this. And I need to do this given that the surface area is 200. So at this time, we're doing it when the surface area, I could just say A, is 200 pi cm squared. We want to do it right there. There are 2 things coming out here. We're dealing with volume. All right. We're dealing with volume. We're dealing with surface area. All right. So we need the formulas for those. So the formula for volume of a sphere is 4/3 pi r cubed. We also know that the total surface area of a cube is 4 pi r squared. All right. So we want to always have some formulas right there so that we can utilize them to go forward. Let's look on how we're going to put this together. I need dr dt. They gave me dv dt. Now I have already had that t at the bottom. All right. So I need to cancel dr dv here, should say. All right, let me fix that. I need a dv at the bottom, and I need a dr at the top. Now, let us first differentiate these, all right? So when you differentiate volume, you're actually going to get some area. And when you differentiate area, you actually get circumference and stuff like those. But let's just go. Let's see what we get. I'm going to differentiate the volume now. So if I go dv, dr, what I'm looking at is 3 times 4/3 pi r squared. And then this 3 will cancel that. So finally, dv dr is actually 4 pi r squared. all right? 4 pi r squared. Now, if you look at this, I need dv dr. This is dr dv. I need dv dr. I'm going to do is to reciprocate that. So basically then, what I'm going to put together is this. I'm saying that what I really want, dr dt, I have dv dt. If I multiply this though by dv, my bad. All right, good. So if I multiply that by dr, then the v's could cancel, dv could cancel, even dr dt. All right. So then all we're gonna do here, let's plug it in. All right. So this is gonna equal to dv dt, which is what I have as 40. I'm gonna multiply this now by the reciprocation of this. So it's gonna be 1 over 4 pi r squared. But we really want to see the point that we're making. This is right, which is 200. So 4 pi r squared is actually the area of the thing. And they did say they want to do it when the area is at a certain number. So now I'm going to put the area as a substitution, because this is actually 200 pi. That's what they say. So I'm going to put 200 pi here, because that's what I want. I want to know what is the result when the area reaches there. So I have an opportunity there to plug the 200 pi where the 4 pi r squared is, because that is the area, the total surface area. So you could see 40 to itself 1, 40 into this will give me 5. So let me just take my time. I have 1/5 with pi under there. And what is this I'm finding? It says it's going to be centimeter per second. So this is dr dt, which is the rate of change of the radius, right? The rate of the, all right. So this one says we have a gas in a container changes its volume according to the law PV equals C. So I'm going to write this. PV equals C. We got that. All right. Where P is the number of units of pressure, V is the number of units of volume, and C is a constant. Given that P is increasing at a rate of 40 units per second. So what it is that we got? P. So I just got dP dt, and it is increasing at a rate of 40 units per second. All right, so I have that. All right. At the instance when P is 80. So you're saying at the instance when P is 80, they want us to calculate in terms of C. So the response will have a C in it. You could see that the rate of change of volume. So this is it, rate of change of volume. So that means they want me to find the dV dt, right? So this is what I need to find. Now, what I'm going to do is to put together what I have and what I want. So I really want dV dt, right? They gave me dP dt. So the T at the bottom is okay, all right? What I want at the top is to have a dV up here. So dV is going to be here, and I need dP at the bottom, because somehow I could cancel this dP with that dP, and I'm left with dV at the top and dt at the bottom. So that's where I'm finding the connected rate of change like right now. So what I'm going to do now is to take, because I have this already. This is 40 right there, right? So what I'm going to have to do is to take this formula here, and then I'm going to set it up in such a way that I could get that dV dP from it. What do you mean? I'm gonna make V the subject, right? So having PV equals C, if I transpose by dividing both sides by P, then we could say that V is actually C over P. Now, if I know that V is equal to C over P, then I could set this up to do my thing. This is the same thing as C, where P would be raised to the -1, because it is a part of the denominator. So it's the inverse, all right, of P right there. So I could now say dV dP is going to equal to that -1 come down, so I have a negative in front of this, so -V, and then I'll end up with P raised to the -2. But what does this really mean? It really means -C over P squared. Putting back the laws of indices there as we move along. So now what I'm looking at now is the fact that we wanna find this. Remember that they want us to do this when P is 80. So now I could find what's going on here. So where P is 80, I'll have -C over 80 squared, right? Which is actually -C over 6400. I'm going to take that as dVdP finally. So what we have now is that 40 will now be multiplied by dVdP, which is -C over 6400. So I want to cancel that out. 40, 6400 divided by 40. I get 160. 40 to itself one time, 40 to this give me 160. So my final answer is -C over 160. I could now conclude that the rate of change of volume is -C over 160. All right. Units per second. And there it is. Thank you for watching Daily Maths Concepts. Drop some likes and some comments, and you could make suggestions about videos that you would like to see. See you next time. Bye-bye.